continue the numericals based on work, and the question is: a cyclist comes to a skidding stop. A cyclist comes to a skidding stop in 10 meters. During this process, the force on the cycle due to the road is 200 Newton. Force on the cycle due to the road. So, road applies a force of friction. Road applies a force of friction on the cycle. So the force on the cycle due to the road is 200 Newton and is directly opposite to the motion. This force is directly opposite to the motion of the cycle. It means this force is the opposite force, means it is the force of friction created by the road. So how much work does the road do on the cycle? The amount of work done by the road on the cycle we have to calculate. So in this case, cyclist is moving in forward direction. Cyclist is moving in the forward direction. So the displacement is in forward direction and the force of friction acting in the opposite direction, opposite to the motion. This is the force of friction which we have given 200 Newton. It means the angle between force and displacement. The angle between force and displacement is 180 degree. Angle between force of friction and the displacement in the first case is 180 degree. And you know the formula for work done. W equals to Fs cos theta, where theta is the angle between force and displacement, and here the angle between force and displacement is 180 degree. The value of theta is 180 degree. So put the value of force is 200 Newton. Displacement S is a cyclist displacement is 10 meter into cos theta, and the value of theta is 180 degree, and cos 180 is equals to minus 1. So minus 200 into 10 into 1, that is minus 2000 joule. And this minus sign shows that this work is done by the force of friction. This work is done by the force of friction. So due to this negative work done, cycle stops. Due to this negative work done, cycle stops. So the answer of the first part is: how much work does the road do on the cycle? So the work done by the road on the cycle is minus 200 joule. And the B part is: how much work does the cycle do on the road? So the force acting on the cycle due to the force of friction is 200 Newton. So according to third law of motion, cycle also applies equal and opposite force on the road. So the force from Newton's third law of motion, from Newton's third law of motion, cycle applies or cycle exert the same force of the same force of 200 Newton on the road. So the force applied by the cycle on the road is 200 Newton. But the road undergoes no displacement. But the road undergo no any displacement. But the road undergo no any displacement. Means when the cycle applies a force of 200 Newton on the road, as the road applies a force of 200 Newton on the cycle, so from Newton's third law, every action there is equal and opposite reaction. So 200 Newton force is applied by the cycle on the road, but after applying the force of 200 Newton, there is no any displacement in the road. So the road undergoes no any displacement. Hence, work done by the cycle. Work done by the cycle on the road. Work done by the cycle on the road is 0. So the answer of the next one is 0. The next question, that is question number 6. A force F equals to 15 plus 0.50x. We have given a force F equals to 15 plus 0.50x. We have given the force F equals to 15 plus 0.50x acts on a particle in the x direction. Acts on a particle in x direction. This much force acts on a particle in x direction, where force is in Newton and x is in meter. Find the work done by this force. Find the work done. Find the work done by this force. Find the work done by this force during a displacement from during a displacement from x equals to 0 to x equals to from x equals to 0 to x equals to 2 meter. We have given the question that if a force of 15 plus 0.50x Newton, where force F is in Newton, x is in meter, acts on a particle in x direction, then we have to calculate the work done by this force during the displacement 0 to 2 meter. When the particle moves from x equals to 0 meter to x equals to 2 meter, then we have to calculate the work done by this force. We know the formula for work done. dW, the small amount of work done, is given by F into dx. If the displacement is a small, then work done will be a small. So dW equals to F into dx. This is the small work done during a small displacement. And to calculate the total work done, we integrate both sides. So integration of dW equals to integration of F dx. Integration of dW equals to integration of F dx. And we have given the limit. The lower limit is given x equals to 0 and upper limit is 2. In this question, we will have to use the concept of integration. So dW equals to integration limit 0 to 2 f into dx and integration of dW. dW is the small work done, and when we integrate the small work done, we get total work done W. 0 to 2 integration 0 to 2. Put the value of F, and the value of force is 15 plus 0.50x and dx. Now we separate the terms. So 15 outside, integration 0 to 2 dx plus 0.50 constant term taking outside, integration 0 to 2 x dx. Now integrate the expression. So 15 integration of dx is x. Integration of dx is x, and limit from 0 to 2 plus 0.50 integration of x dx. This is x square by 2 and limit from 0 to 2. Now we will have to put the limit, and the procedure to put the limit is at the place of x. First we put the upper limit, then we put the minus sign, and then we put the lower limit at the place of x. So work done W equals to 15, and at the place of x we have to write the upper limit at the place of x. So 2, and put the minus sign, and at the place of x we put the lower limit plus 0.50, and this 2 is also constant which should be taken outside, and x square at the place of x we put 2, so 2 the square minus at the place of x again we put 0, so 0 the square. So it becomes 15 into 2, 30 plus 0.50 divided by 2, 0.25 into 4. And 30 plus 0.25 multiplied by 4 is 1. So the result is 31 joule. So the work done by this force during the displacement from x equals to 0 to x equals to 2 meter, the work done is 31 joule. So in this question we had given the force and we have to calculate the displacement work done during the displacement from x equals to 0 to x equals to 2 meters. So we use the formula, a small amount of work done dW is given by F into dx. Then for finding the total integration, we integrated both sides. Integration of dW is W and integration limit 0 to 2, the value of F dx. Then we separate the terms and integration of x dx. There is formula for integration of dx equals to x and integration of x dx. So this will be integrated on the formula x raised to the power n plus 1. At the place of 1 there is, at the place of n there is 1. So x raised to the power n plus 1 upon n plus 1 means x square by 2. So integration of x dx is x square by 2. Then we put the limit. First we put the upper limit, then minus sign, then at the place of x we put the lower limit. The next question. A body moves from point A to B. A body moves from point A to B under the action of a force shown in the figure. There is a graph between force and displacement. We have given in figure, there is a graph between force and displacement. This is the displacement axis and y-axis is taken as force axis. Force is in Newton and displacement x is in meter. 2, 4. We have given the graph. This is the graph between force and displacement. And the points are A, starting point A, and this is the point B. Graph between force and displacement. So a body moves from point A to B. A body moves from point A to B under the action of a force. Force F is in Newton and distance x is in meter. What is the amount of work done? We have to calculate the amount of work done. Work done in moving a body from point A to B. Work done by the force in moving a body from A to B. So work done in moving a body from this point to this point is equal to the area bounded by the graph. So the area bounded by the graph is a rectangle. So work done in moving from this point to this point, we will have to calculate the area of this rectangle. Similarly, work done by the force in moving from this point to this point is equals to area bounded by this graph, means the graph of the area of the trapezium. Then the work done by the force in moving from this point to this point is again, this is the trapezium. So the area of trapezium is equals to the work done by the force in moving from one point to another. And the same way, work done in moving from one point to another is equals to area of the rectangle. So the work done from A to B, W equals to area of rectangle, name it C, D and E. So work done in this case in going from A to C. So W equals to work done in going from A to C plus work done in going from C to D, and this is the total work done. So WAC plus WCD plus WDE, work done in going from point D to E, plus work done in going from point E to B, and work done in going from A to C is found by finding the area of the rectangle 1AC2. This is the rectangle and its area is length into breadth. This length is 2, breadth is 1. So 2 into 1 plus area from C to D in going from C to D. So this figure is a trapezium and area of trapezium is half into height. Height means this distance from 2 to 3. Separation is 1. Half into height into sum of parallel sides. This distance is 2 and this is 4. So sum of these two parallel sides, 2 plus 4, 6. Plus work done in going from D to E. Half into height into sum of parallel sides. So 1 by 2 into, again height is 1 and sum of parallel sides means 4 plus 3. 4 plus 3, 7. Then work done in going from E to B. This is the rectangle. So length into breadth. The length is 3 and breadth is 1. So 3 into 1. So 2 plus 3 plus, this is 3.5 and plus 3. So 11.5 joule is the total work done in going from point A to B. And if a force acting on the particle at point A, then the particle covers the path. It goes from A to C, C to D, D to E and E to B. And in this period, the total work done by the force is 11.5 joule. So this topic work we have completed. In next video we discuss about energy.